This video is about understanding the architecture of Wasserstein GAN or WGAN as it's popularly known, and in the next video that's coming up tomorrow, I will implement WGAN from scratch with Pytorch. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. One more thing, that over the next month, I will do many GAN or generative adversarial network implementation from scratch with Pytorch. So do subscribe, because you hitting the subscribe button is what keeps me motivated to do this. Let's start. So here I'm looking at the original paper of Wasserstein GAN that was published in December 2017 by Martin Orzowski, Soumit Chintala and Leon Botu. This paper is superbly mathematics savvy, lots of equation across the paper, but nothing to get scared of because the underlying architecture is not that complex really. Basically, Wasserstein GAN or WGAN is an extension of the regular GAN that seeks an alternate way of training the generator model to better approximate the distribution of data observed in a given training dataset. So, Wasserstein GAN is a type of generative adversarial network that minimizes an approximation of the Earth's mover distance or EM distance rather than the Jensen-Shannon divergence as in the original GAN formulation. So here is an example comparing a normal regular GAN architecture on the top left corner, and on the bottom right I have a WGAN architecture. And one important factor to note here, how the discriminator is different between WGAN and a normal GAN. So in the normal GAN, when the discriminator gets its input both from the real samples, that is real input data of images, and also the fake images generated by the generator model, then the discriminator outputs either true or false, that is fake or real. It's a binary output 0 1. But in WGAN, the discriminator does not actually classify instances. Rather, here for each instance the discriminator outputs a number. This number does not have to be less than 1 or greater than 0, so we cannot use 0.5 as a threshold to decide whether an instance is real or fake. But the discriminator in WGAN training just tries to make the output bigger for real instances and smaller for fake instances. So in WGAN, instead of using the discriminator to classify or predict the probability of generated images as being real or fake, the WGAN changes the discriminator model with a critic that scores the realness or fakeness of a given image. So basically, the discriminator of WGAN just outputs a number, a score. So the core idea of working off WGAN is to utilize two probability distributions. One is the probability distribution of the generator, what you see here, which refers to the distribution from the output of the generator model, and the other is a probability distribution from the real images. So here this is called PR or P data sometimes, and the objective of WGAN is to ensure that both these probability distributions are close to each other so that the output generated is highly realistic and high quality. So now we can see that these two distributions, that is PG and P data, are very far apart, and the purpose after the training of WGAN, what we want to do is to bring them together as close as possible. So these distribution and this one should come close. And to bring these two distributions closer to each other, the fundamental thing we have to measure is the distance between these two distributions. And for calculating the distance between these two probability distributions, the paper suggests we have 4 options. So let's go back to the paper. I'm looking at section 2 under different distances, and for each of the options they have also given the mathematical expression, and in these expressions you will notice two common things or common terms, PR and PG. Here PR represents the probability distributions of the real data and PG represents the probability distributions of the generated fake data. Our first option is total variation distance. Second one is Kullback-Leibler divergence or KL divergence as it's popularly known. And the third one is Jensen-Shannon divergence. So this is the one that's normally used for all regular GAN, like for example DC GAN. And finally, the fourth option is earth mover distance or Wasserstein 1 distance. And in WGAN, this is the distance measurement for calculating the distance between our probability distribution of the real data and the probability distribution of the generated fake data. And the whole purpose of WGAN is to calculate this distance first between the probability distribution of the real data and the probability distribution of fake data, and then make this distance through training as small as possible so that these two distribution comes closer, thereby the fake generated data comes as close to the original data as possible. And to make sense of these earth mover distance or Wasserstein 1 distance, let's look at this image. I have two distributions here, one pile of dirt here and another pile of dirt here. And then there is a tractor to make this pile as close to this as possible. And this is mathematically determined by how much work is needed to move this pile to this pile. So mathematically, or more in formal term, these earth mover distance or Wasserstein distance is defined by the minimum work needed to transform one distribution to another, where work is defined as a product of mass of the distribution that has to be moved and the distance to be moved. And this is the mathematical expression of Wasserstein distance between PR and PG. Here, this term that is the pi, PR and PG within braces is the set of all joint distribution over X and Y such that the marginal distributions are equal to PR and PG. And this term that is gamma XY can be seen as the amount of mass that must be moved from X to Y to transform PR to PG. So, the Wasserstein distance is then the cost of the optimal transport plan to convert PR to PG. And compared to the JS divergence or Jensen-Shannon divergence, the Wasserstein distance has these following advantages, which is the Wasserstein distance is continuous and almost differentiable everywhere, which allows us to train the model to optimality. Then JS divergence locally saturates as the discriminator gets better, thus the gradients become zero and vanishes. So the problem of vanishing gradient or exploding gradients comes into play. Then the Wasserstein distance is a meaningful metric. It converges to zero as the distribution get close to each other and diverges as they get further away. And lastly, the Wasserstein distance as objective function is more stable than using JS divergence. The mode collapse problem is also mitigated when using this distance. So overall, Wasserstein loss or W loss solves some big problems faced by regular GANs like mode collapse and vanishing gradients. But for it to work well, there is a special condition that needs to be met by the critic. So now we will see what the continuity condition on the critic neural network means and why that condition is important when using W loss for training GANs. And I will spend like 5 to 7 minutes of time on this topic because it's so important to understand these, and also this is one of the fundamental building block while architecting your training loop in your implementation. So here is a mathematical expression for Wasserstein loss, and the W loss is a simple expression that computes the difference between the expected values of the critic's output for the real example X and its predictions on the fake example G of Z, and Z here is the noise vector. So the generator tries to minimize this whole expression, trying to get the generative examples to be as close as possible to the real examples. But the critic wants to maximize this whole expression because it wants to differentiate between the reals and the fakes. So the critic wants the distance to be as large as possible. However, for training GANs, WGANs using W loss, the critic has a special condition. And the condition is that the loss function needs to be something called 1 Lipschitz continuous or 1L continuous for short. This condition sounds more sophisticated than it really is, but let's understand what this is. For a function like the critic's neural network to be at 1L continuous, the norm of its gradient needs to be at most 1, What that means is that the slope cannot be greater than 1 at any point. Its gradient cannot be greater than 1. To check if a function is indeed one Lipschitz continuous, for example, in this case, our function is fx equal to x squared, and that's why we get this graph of this function as a parabola. So to check whether this is one Lipschitz continuous, you want to go along every point in this function and make sure its slope is less than or equal to 1, or its gradient is less than or equal to 1. And for doing that, what you can do is we can actually draw two lines, one where the slope is exactly 1 at this certain point that you are evaluating the function, and one where the slope is -1 where you are evaluating our function. You want to make sure that the growth of this function never goes out of bounds from these two lines. And by the phrase out of bound, I mean this area, this green area. The function cannot go out of this green area, because within this green area our condition of 1L continuous is valid, because staying within these lines means that the function is growing linearly. So in our case, this function, which is fx equal to x squared, this is not one Lipschitz continuous, because the function is staying within the green area for only this section, and also pretty much only this section. Otherwise, the rest of the function, all this white area, the white area here, this function is out of bounds of this green area. That means it is growing more than linearly, and this function is not 1L continuous. Let's look at another example here. This is a smooth curved function, and you want to check again every single point on this function before you can determine whether or not this is one Lipschitz continuous. So let's do that. Let's check various points on this function to make sure its slope is less than or equal to 1, or its gradient is less than or equal to 1. And here in this slide we can see that it looks good, that is its gradient is within this bounded green area. Here also the function is within the bounds of the green, and here also it looks good. And let's say you check every point of this function and it never grows more than linearly. That is, every point of this function, the gradient remains within the bounds of this green. In that case, this function is 1L continuous. And so overall, why this condition of 1L continuity is so important for WGAN is because this condition is what ensures that the W loss function is not only continuous and differentiable, but also that it doesn't grow too much and maintain some stability during training. This is what makes the underlying earth mover distance or Wasserstein distance valid, which is what W loss is founded on. This is required for training both the critic and generator's neural network, and it also increases stability because the variation as the GAN learns will be bounded. To recap, the critic uses W loss for training, which needs to be one Lipschitz continuous in order for its underlying earth mover distance comparison between the reals and the fakes to be a valid comparison. Now, in order to satisfy or trying to satisfy this condition during training, there are multiple different methods, and next we will learn a couple of those methods. And the two most prominent and most well-known methods to enforce one Lipschitz continuity are these two: weight clipping and gradient penalty. Let's learn them in detail. But before getting into the details of weight clipping and gradient penalty, let's recall what it means by 1L continuity. So this is the mathematical expression for 1L continuity, and this delta symbol here represents a gradient of fx, and f is the critic function and x is my input image, that is the generated image by the generator. And the whole expression, that is his whole inequation, just represents that the norm of these gradient being less than or equal to 1, and using L2 norm here, because L2 norm is very common, which just means that it's a Euclidean distance that we are interested in. So intuitively, in two dimension, it's that the slope is less than or equal to 1 at every single point of this function. It will remain within these green triangles, and only then this function will be called 1L continuous. And now coming back to the methods for ensuring 1L continuity, the first one is weight clipping. With weight clipping, the weight of the critic's neural network are forced to take values between a fixed interval. After you update the weights during gradient descent, you actually will clip any weights outside of the desired interval. Basically, what that means is that weights over that interval, either too high or too low, will be set to the maximum or minimum amount respectively. That's clipping the weights there. But there is a downside to these way as well. And the downside is that forcing the weights of the critic to remain in a limited range of values could limit the critic's ability to learn and ultimately to update the gradient to perform. Because if the critic cannot take many parameter values, that means it cannot update freely. So weight clipping not only is trying to do a 1L continuity enforcement, but this might also limit the critic too much. Or on the other hand, it might actually limit the critic too little if you do not clip the weights enough. So there's a lot of hyperparameter tuning involved in this case. And now the second method of ensuring one Lipschitz continuity condition, which is gradient penalty. And this is much softer way to do the job. So with gradient penalty, all you need to do is add a regularization term to your loss function, like right here, this term, lambda reg. What this regularization term does to your W loss function is that it penalizes a critic when its gradient norm is higher than 1. The symbol lambda here is just a hyperparameter value of how much to weigh this regularization term against the main loss function. Now, to check the critic gradient at every possible point of the feature space is virtually impossible, or at least not very practical. Instead, with gradient penalty during implementation, all you do is take a sample some points by interpolating between real and fake examples. Let's see what I mean by that. So, for instance, you could sample an image from a set of reals. That is, this is my real image, this is my generated ones. And what I'm doing here is that I'm taking a sample from the real set and also the generated set. And then I can get an intermediate image by interpolating these two images using a random number epsilon. Epsilon here could be a weight of 0.3 for the real one. And then for the generated ones, it would be 1 minus epsilon, that is 0.7 in this case. Now you interpolate between these two images with this weight factor. That would get you an in-between interpolated image, which is this. Let's call these random interpolated image x hat, and it's on x hat that you want to get the critic gradient to be less than or equal to 1. And here is a mathematical expression of the regularization term for capturing what's happening here. So the critic is applied on the x hat. Rather, the x hat is passed as an input to the critic function, and then you get the gradient of the critic prediction on x hat, and then you take the norm of that gradient and you want the norm to be 1. So here I am pretty much saying, hey, can I get the norm of the gradient to be 1 as opposed to at most 1? Because this in fact is penalizing any value outside of 1. And the whole expression is squared distance, so that it penalizes value much more when they are further away from 1. Specifically, that x hat is an intermediate image where it's weighted against the real and fake using epsilon. With this method, you are not strictly enforcing 1L continuity, but you are just encouraging it. This has proven to work well and much better than weight clipping. Now finally, putting it all together, this is a complete expression of the loss function in WGAN with gradient penalty. So first, this part here I am approximating the Earth's mover distance with these main W loss component. This makes WGAN less prone to mode collapse and vanishing gradients. And second is this term, the regularization term, that makes a critic to be 1L continuous for the loss function to be continuous and differentiable. Of course, this is a soft constraint on making the critic one Lipschitz continuous. but it has been shown to be very effective, keeping the norm of the critic close to 1 almost everywhere. And finally, before actually implementing WGAN with Pytorch from scratch, these are the overall architectural key points that we have to keep in mind. The first one is obviously, all our previous discussion was based on these, that we have to bring in weight clipping on the critic to enforce the one Lipschitz continuity conditions. And the way we implement these is with a hyperparameter, that is, the weights of the discriminator must be within a certain range controlled by a hyperparameter named C. Then the next point is updating critic more than the generator. So this is in contrast to what we do in a regular GAN. For example, in DC GAN, the generator and the discriminator model must be updated in equal amounts. Specifically, the discriminator is updated with a half batch of real and half batch of fake samples each iteration, whereas the generator is updated with a single batch of generated samples. But in WGAN here, the critic model must be updated more than the generator model. Specifically, a new hyperparameter is defined to control the number of times that the critic is updated for each update to the generator model, and that hyperparameter normally is named as n_critic. We will see that when we implement that from scratch. And the third point to keep in mind is that WGAN recommends the use of root mean square propagation or RMS prop stochastic gradient descent strategy instead of the Adam optimizer, which is used for DC GAN or regular GAN. And also we use a small learning rate of something like 0.00005. And now one of the most important part in WGAN, which is implementing Wasserstein loss in WGAN. So in WGAN, the critic loss is defined by this expression, that is average critic score on real images minus average critic score on fake images. So mathematically it will be dx minus d of gz, and z here is the noise vector, that is d of so gz will represent the fake images, so d of fake images. And the generator loss will be defined by minus of average critic score on fake images. And the crucial point to note here again, that in WGAN, the discriminator does not produce a probability, rather it produces a pure score. So the output of the critic D does not have to be between 1 and 0. That is this expression here. So the discriminator tries to maximize these expression on the right side. In other words, the discriminator in WGAN tries to maximize the difference between its output on real instances and its output on fake instances. And these strategies in WGAN are implemented following some points, which are these. So first, use linear activation function in the output layer of the critic model instead of a sigmoid. Remember, in a regular GAN, we use sigmoid as a very last step in discriminator. Then use Wasserstein loss to train the critic and generator models that promote larger differences between scores for real and generated images. Then constrain critic model weights to a limited range, that is weight clipping, after each mini batch update, for example between minus 0.01 and between plus 0.01, and this range is defined as a hyperparameter to the training function. We will see that in my next video when we will implement it from scratch. And the last point is, in order to have parameters W lie in a compact space, something simple we can do is clamp the weights to a fixed box. Okay, this is just some more implementation actual code details. The number 4 points is actually just implementation details. So these 3 points are the most important while implementing this architecture. And these are the actual workflow or the actual training steps that I will follow in my next video while implementing WGAN entire architecture from scratch. Let's go through them quickly here, because now that we have gone through all the fundamentals and all the theories, these steps will definitely make sense. So the first part is the critic network is trained on a batch of real data and also on a batch of data generated by the generator. Then the Critic's loss function is arranged such that it estimates a Wasserstein distance, that is maximizes the distance between the two distributions, that is the probability distribution of generated images, that is fake images, and also the distribution from the real image dataset. Then clips its own weights to ensure it is one Lipschitz continuous, and clipping of this own weights is done through a hyperparameter by defining the range within which the weight should be limited. And remember, the Critic's loss is an approximation of the negative Wasserstein distance between the generated distribution and the real data distribution. And why I am saying negative Wasserstein distance, we will see that, and we will actually making sense of that while we will do the implementation in the next video. Then the generator generates a new batch of images from a noise prior or a noise vector, passes these through to the Critic, who then informs the generator of the Wasserstein 1 distance between the true distribution and the distribution of the images that the generator just produced. And it does this via the loss function of the Critic. The Critic's weights are frozen and the error propagates all the way back through to the generator, who then updates its parameters to minimize the Wasserstein distance. And this whole workflow repeats until the loss converges to near zero and the distributions are approximately equal. That is the distribution of the real images and the distribution of the fake images. That pretty much wraps up this architectural understanding video on WGAN. And in the next one that's coming up tomorrow, I will implement WGAN from scratch with Pytorch. So stay tuned. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with Pytorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.